Look at any modern performance car and tell me something. Why are the brakes almost the size of a pizza? And here's the crazy part. The exact upgrade that makes your car stop harder is also quietly making modern performance cars heavier than ever. Let's get into it. First, let's put some numbers on this. A typical brake system on a modern performance car. We're talking about something like a BMW M4, a Porsche 911 Carrera S, or a Corvette Z06. Consists of massive carbon ceramic rotors, multi-piston calipers, mounting hardware, brake lines, and fluid. When you add it all up, you're looking at somewhere between 80 to 120 pounds just in braking components. That's the weight of a small adult human, sitting entirely at the corners of your car. But here's where it gets really interesting. Not all weight is created equal. Engineers obsess over something called unsprung weight. That's the weight of components not supported by the car's suspension. This includes wheels, tires, brake components, and parts of the suspension itself. Every pound of unsprung weight affects the car's dynamics roughly 3 to 5 times more than a pound of weight in the chassis. So those 100 pounds of brakes, they're effectively acting like 300 to 500 pounds of regular weight when it comes to handling, ride quality, and acceleration. Let's look at a real-world example. The latest Porsche 911 GT3 RS comes with carbon ceramic brakes as standard. The front rotors alone are 16 inches in diameter and weigh about 20 pounds each. Compare that to the standard steel rotors on a base 911, which come in at around 25 pounds but are smaller in diameter. The upgraded system adds substantial mass, but it's positioned exactly where you don't want it, at the very edge of the wheel, maximizing rotational inertia. The Ferrari SF90 Stradale tells an even more extreme story. This hybrid hypercar produces 986 horsepower, but it weighs over 3,700 pounds. The carbon ceramic brake system alone accounts for nearly 100 pounds of that figure. Ferrari engineers admitted in interviews that the brakes were one of the few areas where they simply couldn't compromise. The car's performance envelope demanded that stopping power, regardless of the weight penalty. So why are brakes getting so absurdly large? The answer comes down to 3 main factors: vehicle weight, tire grip, and performance expectations. Modern performance cars are significantly heavier than their predecessors. A 1995 Porsche 911 Carrera weighed around 2,900 pounds. The 2024 equivalent? Nearly 3,500 pounds. And that's before you add the upgraded brake package. This weight gain comes from safety features, technology, luxury amenities, and increasingly complex powertrains, especially in hybrid models. Heavier cars need more braking force to stop in the same distance, which means bigger rotors and more aggressive caliper designs. Then there's tire technology. Modern performance tires generate absolutely insane levels of grip. A set of Michelin Pilot Sport Cup 2s or Pirelli P0 Trofeo RS can generate over 1.4 G of lateral acceleration on the right car. That's extraordinary, but here's the catch. Your brakes need to match that grip level. If your tires can generate 1.4 G of deceleration, but your brakes can only provide 1.0 G, you're leaving performance on the table. Worse, if you're on a track doing repeated hard stops, inadequate brakes will fade, and suddenly your massive grip advantage becomes a liability as you blow past your braking point. The third factor is customer expectation and regulatory pressure. Performance car buyers expect their vehicles to handle repeated track sessions without brake fade. This wasn't always the case. 30 years ago, if you took your sports car to the track and experienced brake fade after a few laps, that was considered normal. Today, it's unacceptable. Car magazines, YouTube reviewers, and customers all expect consistent, fade-free braking performance. Additionally, regulatory bodies have increased minimum braking standards, forcing manufacturers to over-engineer their systems to ensure compliance with a safety margin. The result? A performance arms race where each generation needs bigger brakes to handle the increased weight, match the improved tires, and meet heightened expectations, creating a vicious cycle that keeps adding pounds. Here's where we need to talk about why brake weight is so particularly damaging to performance. It all comes down to rotational inertia, specifically, how the location of mass affects how easy or hard it is to accelerate or change the rotation speed of a wheel. Think about an ice skater doing a spin. When they pull their arms in close to their body, they spin faster. When they extend their arms outward, they slow down. This is rotational inertia in action. Mass that's farther from the center of rotation has a much greater effect on how hard it is to change that rotation speed. Your brake rotors sit at the very edge of your wheel, as far from the center as possible. This means they have maximum impact on rotational inertia. When you're accelerating, the engine isn't just fighting to move the car forward. It's also fighting to spin up that rotational mass. The heavier your wheels, tires, and brakes, the more energy is wasted just getting them spinning. Energy that could otherwise be accelerating the car forward. Testing by automotive engineers has shown that removing just 10 pounds of rotational mass from all four corners can improve quarter-mile times by 0.1 to 0.15 seconds. That's the same improvement you might get from adding 30 to 40 horsepower to the engine. In other words, reducing brake weight is one of the most efficient performance modifications you can make. But the damage goes beyond straight-line acceleration. Heavy brakes negatively affect suspension compliance. Your suspension's job is to keep the tires in contact with the road surface over bumps and imperfections. When unsprung weight increases, the suspension has to work harder to control that mass. The result? Reduced grip over rough surfaces, harsher ride quality, and slower lap times on anything other than a perfectly smooth track. The industry's answer to the weight problem has been carbon ceramic brakes. These high-tech components promise massive weight savings, typically 40 to 50% less than equivalent steel rotors, along with better heat resistance and virtually zero fade under track conditions. On paper, it's the perfect solution. Carbon ceramic rotors can withstand temperatures exceeding 1,800 degrees Fahrenheit without fading. They don't warp. They last significantly longer than steel rotors, often outliving the car itself in normal driving conditions. And yes, they're substantially lighter. A complete carbon ceramic brake system might weigh 50 pounds less than a comparable steel setup. So what's the problem? Three things: cost, cold performance, and diminishing returns. Cost is the most obvious barrier. Carbon ceramic brakes are hideously expensive. On a Porsche 911, the carbon ceramic brake option costs around $9,000. On a Ferrari, you're looking at $15,000 or more. For most buyers, even enthusiasts who plan to track their cars, the price-to-performance ratio doesn't make sense, especially when high-performance steel brakes with proper cooling can handle the majority of track work. Then there's cold performance. Carbon ceramic brakes don't work well until they reach operating temperature. In daily driving, especially in cold weather, they can feel grabby, inconsistent, and generate annoying squealing noises. Many owners of high-end performance cars actually regret the carbon ceramic option because the brakes feel worse in the 95% of driving that happens on the street. But the biggest issue is diminishing returns. Yes, carbon ceramic brakes save weight, but there's still large, heavy components at the corners of the car. You're still dealing with massive 16-inch rotors and multi-piston calipers. The fundamental problem, lots of mass at the worst possible location, hasn't been solved. It's been mitigated, but not eliminated. Let's talk about what this weight penalty actually means for how a car drives. The effects are subtle but profound, and they touch every aspect of dynamic performance. First, there's steering feel. Heavy brakes increase the gyroscopic effect of the rotating wheels. When you turn the steering wheel, you're fighting against this gyroscopic force. The result is steering that feels heavier and less immediate. This is one reason why modern performance cars often feel less communicative than lighter, older sports cars. The steering rack is processing more inertia from the wheels. Then there's transitional behavior, how quickly a car changes direction. Think about a slalom course or a tight chicane on a racetrack. The car needs to rapidly shift weight from one side to the other. Heavy brakes resist this motion. They slow down the car's ability to react to steering inputs. A lighter car with smaller brakes might have less outright grip, but it can often set faster lap times on a technical course because it changes direction more quickly. The effects compound under hard driving. On a long track day, heavy brakes contribute to overheating brake fluid, fading pad compounds, even with carbon ceramic rotors, and increased wear on suspension components. The extra unsprung weight hammers the dampers, bushings, and wheel bearings harder with every bump and curb strike. Professional race teams understand this intimately. In series like GT3 racing, where regulations allow it, teams spend enormous resources minimizing brake weight. They use exotic materials, hollow mounting bolts, and titanium caliper pistons, anything to shave ounces. Because in racing, where cars are often separated by tenths of a second per lap, brake weight is one of the few areas where you can find significant, repeatable gains. So what's the solution? Some manufacturers are starting to push back against the bigger is better brake mentality. Porsche's GT department has become more selective about brake sizing. The 718 Cayman GT4 RS, despite being a serious track weapon, uses slightly smaller rotors than you might expect, paired with aggressive cooling ducts and optimized pad compounds. The result is a car that weighs less and handles better, with brakes that are still more than adequate for sustained track use. Lotus has taken an even more radical approach with the Emira. They've gone back to basics, relatively modest brake sizes, careful attention to cooling airflow, and an obsessive focus on keeping unsprung weight low. The result is a car that might not have the peak stopping power of a heavier competitor, but delivers a more balanced, engaging driving experience. The real innovation is happening in materials science and thermal management. Companies are developing hybrid rotors, steel friction surfaces with aluminum or composite hats that save weight while maintaining performance. Others are working on improved brake cooling systems that allow smaller rotors to handle higher heat loads without fade. We're also seeing a shift in philosophy. Some engineers are asking whether we've reached the point of diminishing returns. Do we really need brakes that can handle 20 consecutive maximum effort stops when most track sessions involve 5 to 8 hot laps before cooling down? Is it worth carrying an extra 40 pounds of brake capacity that will only be used 1% of the time? The question isn't whether big brakes are necessary. They often are. The question is whether we've gone too far, prioritizing numbers on a spec sheet over the driving experience. What do you think? Drop a comment below. And if you enjoyed this deep dive, hit that subscribe button. We've got more engineering deep dives coming your way.